Hey there everyone, so we're going to start with chapter 8 here. This one is about naming. We call this chapter chemical nomenclature. That's just a fancy way of saying how to name chemicals. Alright, so we're going to start off with a couple things that are hopefully kind of familiar to us. This one, for example, this one is the gas that we breathe out. So that we know as carbon dioxide. This one is a gas that kills people if you leave your garage closed with your car on. So that, of course, is called carbon monoxide. Okay, so they're similar because they're made out of the same elements, but the difference between them is that one of them has 2 oxygen instead of 1. And so we indicate that using this prefix here. So di as a prefix means 2. So every time we have 2 atoms in a covalent compound, these are all covalent compounds. Every time we have 2 atoms, we're going to call it di, and then we name the atom. Another thing that's similar about it is IDE. The second word, oxygen, has been transformed. So a second element gets transformed, where we kind of ignore the ending here and turn it into IDE. So that prefix IDE is the chemistry way of saying that it's an element. Just oxygen connected to a carbon. Okay. The next one we would name phosphorus because it's P. This one's a tricky one to spell. Okay, because many people want to write it like this, or even with an F in the middle. This is wrong. As I'm working through these, or when you're doing your homework, if you can't remember, oh, I did it again. There we go. If you can't remember how to spell something, or maybe you can't remember the symbol for it, there is an alphabetical list of elements at the very last page of your book. So that is a handy reference for while you're doing naming. Ultimately, you want to get to a point where most of the common things you recognize and you can spell easily, because of course on your final exam you're not going to have your textbook. Alright, so we have phosphorus, and the next element is chlorine, Cl. That's going to transform to chloride, just like carbon dioxide. Okay. There's 3 atoms here, 3 chlorine atoms, so we got to use the prefix for 3. So 3 is tri. Okay? So 3, like tricycle or triangle. So phosphorus trichloride, that's what we've got here. This, of course, is water, but it has a scientific name. It's kind of a fun one. There's 2 hydrogens, so we're going to use that word di again. Hydrogen's written first, so we're going to write it first in the name. So dihydrogen. And then oxygen is second, and since it's second, its ending changes to IDE, so oxide, dihydrogen oxide. Sometimes you'll see it listed, you can even search for this. If you search for dihydrogen monoxide safety sheet, it comes up with this joke material safety sheet that tells you how terrible water is. It says 100% of the people that come in contact with dihydrogen monoxide die, or that inhalation causes death. You know, it sounds like a really terrible chemical, so you should look that up. So it's a little inside joke you can play on people, because dihydrogen monoxide, of course, is water, and yes, 100% of people come in contact with water and die. Well, 100% of people die eventually, and 100% of people come in contact with water, so both of those statements are true. All right, but it's just a funny little joke about people who don't know how to name chemicals. So now you're on the inside part of that joke. Okay, so the technical term for water is dihydrogen oxide, or you can say dihydrogen monoxide. So the mono is optional. Mono means 1 atom. You don't have to say it. If you don't have a prefix, we assume it's just 1 atom. So like up here, you could say carbon oxide, and that would technically be okay. You don't have to say mono. We do because it sounds better, but other than that, there's no particular reason for it. This bottom one I'd like you to try out for yourself. The one tip I'll tell you is that the number 5 has a prefix which is based on a shape that has 5 sides. Okay, so try to follow these rules and name this element, this compound rather. Pause the video and do it now, because I notice a lot of you are forgetting to go back into your notes. So do that now. This is going to be graded. So pause it. Okay, so the next slide tells us about what we just did. This is the rules for what we just did. When we have binary covalent compounds, that's a fancy way of saying, oh my goodness, let's go back. I don't know what just happened. Binary covalent compounds is a fancy way of saying two different elements, binary means two, that are covalently bonded. So just a reminder from chapter 6, this should be familiar by now. Covalent means non-metals. And you should know where those are on the periodic table. Okay? So, two different non-metal things. That's how we name them. We name them sort of in order of how they're read on the periodic table. So carbon and oxygen. Carbon is over here, oxygen's right here. We read carbon monoxide because carbon is on the left of the periodic table and oxygen's farther right. If you have halogens, tell me what group that's in, by the way. You should know that from the last chapter. If you have halogens and oxygen together, we switch it. Even though the halogens are over here, all right, we still write oxygen last. That's one exception to our usual reading from left to right on the periodic table. If you happen to have two elements in the same group, say I have sulfur and oxygen in a compound, the one that is lowered down is first. So sulfur is in a lower period than oxygen. So sulfur gets written first, and it's going to be named first. Okay. The name of that, by the way, would be sulfur dioxide. Okay. So those prefixes, the Greek prefixes, are used to show how many of each element. I could say monosulfur dioxide. That would be okay too. And then finally, we change the ending of the second thing to IDE. All right, so here's the prefixes. We need to know these, so you need to make some flashcards and practice them. There's only a few that you probably don't already know. Most people know mono, di, and tri, or they can figure out mono anyway. It's kind of like mono e mono. It doesn't mean man versus man. What it means is one versus one, one-on-one competition. So, you know, two women can go mono e mono. All right, so that's often misused in our language, but mono means one. Di is 2, tri is 3. Okay. 4 atoms. This one's a little tricky for some people, so really focus on it, on making sure you know this prefix. 4 atoms. It's not quad. It has nothing to do with ATVs. Okay. 4 atoms is tetra. So technically, a square is a tetragon. 4-sided figure. Gon means figure. Tetragon. 5 atoms is penta. Like pentagon. 6 is hexa, just like a hexagon. 7 we don't normally use in regular, geometry or shapes or anything, but it's hepta, H-E-P-T-A. Heptagon is a 7-sided figure, which does exist. You just don't see them very often. 8 is familiar. It's octo, or octa, really. An octagon has 8 sides. Octomom had 8 twins. Wait, they're not twins. Octuplets, right? Oct, that keeps coming up. So 8 babies all at once is oct. 9 is a little unusual, so I'm going to highlight that one as well. This one is nana. A nonagon would be a 9-sided figure. And finally, 10 is deca. 10 means deca. So remember that, make some flashcards. Pause the video, make some flashcards. Be quizzing yourself on that regularly. You should know these cold by next week easily. Okay, so if we name the following compound, N2O3, I want you to do this to be graded. Pause the video and do it now so you don't have to remember to come back later. I'll wait. Okay, you're also going to do this one. They're both going to be graded. I want you to use those rules we just learned and the prefixes together to figure out the answer here. Okay, so that was covalent compounds, and now we're going to talk about ionic compounds. So ionic compounds are usually a metal and a nonmetal. Okay, we call these salts also ionic salts. So the word salt, like table salt, comes from chemistry. That's a chemical word. So here's table salt, NaCl. The formal name of this stuff, it's pretty easy. You name from left to right on the periodic table, and sodium's all the way on the left. So we're going to name sodium first. And then this is chlorine, and just like in the binary covalence, that becomes IDE, so chloride. This one's calcium. You should remember the elements. We had that quiz on elements 1 through 20, so these are all within that range. Should be familiar to you. If it's not, make some flashcards. Now here, we do not say calcium dichloride because, as it turns out, we're not allowed to use those Greek prefixes when there's a metal. So if there's a metal here, we can't do the Greek prefixes. It's a rule. I don't know why it's a rule, but it is. So we're going to follow it. Okay. So we're going to just call that calcium chloride. And as it turns out, it has to have 2 chlorine in it, because if we look at our periodic table, right in the upper right-hand corner of each box, it has little charges, and that is a reflection of how many electrons something can gain or lose. So calcium, in our periodic table, it says calcium with a 2+ in the corner. That's because calcium's in group 2, so it loses 2 electrons. Chlorine has a whole bunch of charges listed, but the primary one is -1. That's because chlorine has 7 electrons. It's going to gain 1 more, and then it'll have all 8 electrons that it needs. Sorry, something's going crazy here. So anyway, we have to have 2 chlorine because 1 of those electrons went to this chlorine, but that means I got to have a second chlorine for the other electron to go into. And so you can think of this in 2 ways. It's a Lewis dot structure sort of thinking, you know, where we got to have our 8 electrons to make the chlorine happy, and so that means 1 of them came from calcium. We got to have 2 chlorines to do that. Or you can think about it in terms of mathematically. These charges need to cancel each other out. They should add up to 0. So 2 plus -1 only gives us -1. So that means I need to multiply this by 2. Okay, and so I would put that 2 right there. Okay, so that's how you predict formulas. It's based on our Lewis dot structures, just like we practiced in the last chapter. This one, magnesium, is also in group 2, so it's also going to have 2 electrons to lose, so it'll become +2. Chlorine can still only take 1 at a time, so we got to have 2 different chlorine atoms to make that a thing. I don't use the prefix here though because I have a metal, so that means I'm not allowed. Okay? So not that different from what we learned with the covalent stuff. Now, if we apply that logic here, we're going to see iron is Fe. Here's a joke to help you remember that. You get it? It's Iron Man. Okay, so iron is Fe, and this is oxygen, but it becomes oxide because it's the second element. Okay, so far we followed the same rules as we did before. Here, this one is iron and oxygen again, so it's iron oxide as well. Now we have a problem because these 2 substances are totally different. This one is red. Well, not quite that red, but it's the color of your truck that you drive all winter in upstate New York. Or it's the color of Mars. That's what gives Mars its color. This other one, this one is black. They're both a kind of rust. It's a metal oxide, we call it. They're both a kind of rust. One of them is red and one of them is black. And they're completely different in their melting point and their different properties. So we have to have a way of telling these apart. And as it turns out, the best way to tell them apart is to know what charge they have. So metals can be multiple charges. Let's take a look at the periodic table at iron. Okay, so this one looks slightly different from the version that you have, but it has the same information in it. You can see iron is element number 26, and it has +3 and +2 written here, and yours is going to be vertically, like up and down this way. Those are the two possible charges that iron can have. And so the reason that we have two different compounds here is because one of these is going to be Fe with a 2+ charge, and one of them has got to be 3+. Now, to figure out which is which, we have to know something about what it's connected to. This oxygen is the important bit. So if we look at oxygen on your periodic table, it has a -2 charge. Oxygen always wants to take 2 electrons all the time. It's the only thing it does. So that means, at least under normal conditions, for our class's purpose, anyway. So that means the oxygen is going to be a -2. If I have one oxygen and one iron, then that one has to be a +2. So this one, in this version, this is Fe with a 2+ charge. In order to show that in the name, we're going to change it by putting parentheses after the iron, and then the Roman numeral for 2. The oxide stays the same. There's a space between them. They're two different words. So iron 2 oxide is how we'd read this one. Here, this is a little more complex. I have 3 oxygens, and each one has a charge of -2. So that's going to add up to a total negative charge of -6. I have 2 irons. I want all those irons to add up to cancel out this -6. It's going to be +6. But I have 2 of them, so I'm going to divide. What this tells me is that each iron has to hold a charge of 3+. In other words, each iron has to give up 3 electrons to the oxygens. So if we draw a picture of the Lewis structure here, this is an ionic thing because it's a metal and a nonmetal, and we're saying we have oxygen and iron. Here's why there's 2 oxygens and 3 oxygens and 2 iron. This first one's going to give 1 electron to this oxygen and then 1 to here. So that oxygen's happy. It's got 8. I still have 1 extra electron on this iron, so we're going to have to find another one cruising around to give that to. So now this iron is happy. So we're happy here, happy here. This iron is going to also donate 1. So now this oxygen's good. But we need a third oxygen because I still have 2 electrons on that iron. I gotta get rid of this one and I gotta get rid of this one. Now this is happy and this is happy. So you can draw these Lewis structures to help you figure out the charges if it helps you to visualize it that way. But our iron here is going to be +3 and our oxygen is -2. And the only way to get these to balance is if I got 2 irons, so that's a +6, and a 3 oxygen, so that's a -2. So I'm going to change my formula here to have Roman numeral 3 right after iron. That's the correct way to name these. So iron 3 oxide is red, iron 2 oxide is black. Okay. So here's the rules that we just used, and a little joke for you. This is such a hilarious chapter, 2 jokes at once. Right, different naming strategies in different sciences. And it's kind of true, because like Neil deGrasse Tyson gave a talk here. He's a famous astrophysicist from New York City, and he said that in physics, they just name things for what they are. Okay, so like for example, the most important thing in physics, he said, was the Big Bang, and that's what they think it was, just a giant bang. In chemistry, we put all kinds of weird numbers and hyphens and commas and whatever. It's craziness. And then in biology, they always have fancy, usually Latin-based names. So it's just a little joke here. All right, so what I want you to do with this slide is somewhere on here, tell me what the names of these things are. All right. Note that you only have to use the Roman numeral if your metal has more than one charge. Oxidation state and charge mean the same thing. If it doesn't have more than one choice, you don't need to use a Roman numeral. Bottom line is you can't use prefixes. Greek prefixes are not allowed here because these have metals in them. So pause it and go ahead and make sure you do that. Don't skip it. Okay, so now the next thing is I want to tell you about something called the classical naming system. What we're learning is what we're going to be testing on is called the modern naming system. This is regulated or invented, if you want to say, by an organization. It's not a company. An organization called the International Union of Pure and Applied Chemistry. So they decide on how to name all chemicals, and that has ramifications for how food is made and drugs and medicines, everything like that. They kind of control that sort of naming, and also metric system falls into their category. The IUPAC system is predictable and relatively easy to learn. The classical naming system is full of all kinds of exceptions and weird things. Like, for example, Fe2+ would be called ferrous. So FeCl2 would be called ferrous chloride in the old way. Weirdly, if you have copper 2, it is not called cuprous, copper cuprous. It's actually called cupric. The pattern, there is a pattern, it's a little subtle. The charges don't really match, but the pattern is that copper can be a +1 or a +2. So cuprous means that you have a +1. It's the lower charge. OUS means lower charge. IC means higher charge in this context. We're not going to quiz you on this, but you're going to run into it in your careers. You're going to run into different medicines and cleaners and different things that have these funny endings on it that you're going to be confused by. The main thing to do is to look it up. All right? We're not going to use these in lab or anything. I just want you to be aware that they exist, okay? But we're not going to quiz on it or anything. We're going to focus on learning the modern, more systematic method. Now there's two cations. Remember, cations mean positively charged. Cations are positive. Okay? There's two cations that are not metals that are important. One of them is ammonium. Ammonium is positively charged, so it's a cation. And if you remember, we did this Lewis structure in chapter 7, and it looks something like this. So ammonia with a positive charge because it lost an electron. Ammonium here is a cation. Another one is hydronium ion. It's an oxygen with 3 hydrogens attached to it. We're going to run into this one quite a lot next semester. For this semester, ammonium is one of them. The name for this is on the back of your periodic table. So if you forget, also the formula, if you forget what ammonium is, you should look there when you see that name and you need to translate it. All right, so this compound would be called copper 2 chloride because it's chlorine, and chlorine is a -1. And I have 2 of those, so that means I have a total negative charge of -2. So I got to have a +2 to compensate for that. This one is a little bit similar, except that instead of 1 element, we have 2. So this is not a binary thing. This is 3 different elements: copper, sulfur, and oxygen. We never name things. Like, you're going to be tempted to just do this: copper, sulfur, oxide, or maybe tetraoxide or something like that. This is wrong. If you have 3 different elements stacked together like that, that is not the correct name. So watch out for that. Avoid the temptation, because that's not a thing that exists. What does exist is to call it copper. We're probably going to need Roman numerals because copper has a choice. And then look on the back of the periodic table and find out what SO4 is. As it turns out, if you look there, it's got a -2 charge. It says SO4, 2-, and the name of it is sulfate. All right, so if this has a -2 charge, that means the copper is a +2 in this one as well. So we can write copper 2 sulfate. This is the stuff we used in lab as a catalyst. All right, our catalyst is something that just makes the reaction happen faster. So it's not a reactant or a product. It doesn't participate in the reaction, so I wanted to highlight that because we used it in lab. All right. Okay, so using that same idea, what would we name this one? Okay, so that's graded. Go ahead and pause it and take care of that. Okay, so let's try some more together. So this is Fe, so we said that was iron. Iron has a choice, so I'm going to have to use Roman numerals at some point. And then this thing, PO4, is more than, we got more than 2 atoms here. We got 3 total: iron, phosphorus, and oxygen. So I flip over the periodic table, and we find out the name of PO4 3- is phosphate. Okay, so 3- here, I'm going to guess that since iron can either be +2 or +3, this is probably a +2 because of the simple fact that if it was 3-, you'd have one of each, and we don't. I have 2 phosphates, so that's going to be -6. -6 divided by the number of iron we have gives us +2. So I was correct. It is iron 2-phosphate. All right, so I want you to name the rest. I highlighted here that this is a special group, so that's on the back of your periodic table. You don't have to change the name or the ending or anything. You just write down whatever this says after we've established what the metal is. So same thing here. This is a polyatomic group. Poly meaning many atoms. We have 3 different atoms in this, so we've got a polyatomic. We've got to flip it over and find it. Okay, so do the rest of these. I'm not grading for correctness here. I'm just trying to see if you give it a shot or not. So all you got to do is try. So pause it and give it a shot. Okay, so what we've done here is we've used this pretty handy little flow chart. This is not from your textbook. I made this. So that means if you have suggestions for how to make this clearer, please share it with me, and I will update it for future generations of classes. Okay, but so basically the way to approach this is if I'm confronted with a name, let's say I get this one. This is a name I get. And I have to translate this, okay? So that's one of the that's one of the types of questions we're going to get quite frequently. And so I know that Na is sodium, but other than that I'm not sure what to do. So here's what we can do. Is the first letter, the first element in your formula an H? No, that's an Na, so we're going to go down this pathway. We haven't talked about any that start with H. Those are called acids, and that's going to be filling in the top of this chart here in a minute. All right, so no, none of them are H. It's an Na. So I'm going to go down here. Is it a binary compound? Binary means 2 atoms. Well, no, I got 3. I've got sodium, sulfur, and oxygen, so no. Then I say, okay, polyatomic ion or ions present. Oh, I can have more than one. Well, that's interesting. This question is answered by the back of the periodic table. All of the polyatomic ions we're ever going to use are going to be on there. So if it's not a binary compound, you should flip over the periodic table and check it out. Okay, that's going to help us out. So I'm going to look over there, and it looks like SO4 is a polyatomic. So yes, we're going to name it like a binary compound, but we're going to keep the ending the way it is. So SO4 is sulfate, so we're going to keep it as sulfate. If it were a binary compound, we would have asked, is there a metal present? The answer is yes. Sodium's a metal. Does the metal form more than one cation? So I got to look at the front of the periodic table to answer that question. All right, so here, this is the back. And up here, we're going to use the front. We're going to look at the sodium in this case, and it just says Na+. So no, oh, I'm sorry. I put these in the wrong space. These are supposed to be down here. So Na+ is the only kind of cation that sodium can do. So no. So we're going to name the cation. And normally we would change the ending to IDE, but our instructions from before say to leave it. So we're just going to name it sodium, which is a cation, sulfate. Okay. So I'm going to give you just a couple more to practice with. Try to use this chart. See if it helps you to see how these rules are related to each other. Here's one. And we're going to do one more. Okay, so tell me the names of these things, all right? Pause it and go ahead and do that. All right, so now the next category. So we said that the other half of this flow chart is going to be when there's an H in the front. When there's an H in the front, it means that it's an acid. Okay. So for example, in the lab we saw HCl. It was called hydrochloric acid. Right in the lab we saw that just this week, or maybe last week. Well, one of the interesting, it says this little thing in parentheses, when it's dissolved in water, it means solution. Solution always means that we use the symbol AQ after it. So HCl should be written in a formula as HClAQ because it's an acid. All acids have hydrogen in the beginning and AQ as the state of matter. If we have HCl gas, which is like pure hydrochloric, we don't call it hydrochloric anymore, actually. We call it just like a binary compound. We would just name it hydrogen chloride. So we have to be a little bit careful. Acids are always going to be AQ. If I don't see AQ, it's a gas or a liquid or a solid, then I want to name it just like the binary compounds were. So that's a little thing to watch out for. We use the back of the periodic table to help with this part as well, because we need to know polyatomic endings, ITE or ATE, to tell how to name the acid. So for example, and by the way, you'll notice all of these have oxygen. The polyatomic one acids do. We call them oxyacids for that reason. That means that the prefix of hydro that we had is not allowed. Hydro refers to not having any oxygen. We have all oxygen present here. So this is a really important rule. We don't want to mix up things that are like hydro and things that are not. Okay, so no hydro. Instead, what we do is we look up the name for this thing on the back of our periodic table, and we find ClO4 minus about 1/3 of the way down our list, and we see that that stuff is called perchlorate. So the ending on that one is an ATE ending. ATE ending right here. So whenever we have ATE, ATE becomes ic acid. So what we're going to do is take the same word, perchlor. That ATE part goes away and it becomes ic acid. I remember this by just, this is kind of silly, but a student told me this once and it sticks. 8 is icky. All right, so 8 is icky. So perchloric acid is the name of HClO4. And I know it's an acid because I got that H in the front, so that's the first thing to realize. H2SO4, so we're an acid because it's aqueous and there's an H in front. SO4 is also on the back of that table. We call that a sulfate. So ATE becomes ic. So this is actually called sulfuric acid. Now, if you wrote sulfic acid, you don't add the UR, that's okay. There's just some weird things about the way we speak English. We don't like having just sulfic. It doesn't sound right to people. So we say sulfuric acid. Okay. So now I want you to try these two using our rules. Remember that 8 is icky. Ite becomes OUS, acid. All right, so go ahead and try those two. All right, so this is the complete flow chart. And so a lot of people find this very helpful in learning naming because there's so many different rules and you have to learn how to break it down. Okay, if you invent your own flow chart, please do share that with the class. You can get a few extra credit points for that kind of work. If it's different from mine and the way that you think about these rules is different from me, that's okay. So let's share that knowledge. But essentially, if we have a random acid name, let's say, I don't know, oops. Let's just make up one. Let's say it's, we'll go with H2CO3, AQ. Okay, so we practiced the bottom part. That's the same as we practiced before, but this top part is a little different. The first letter is an H, so yes. The compound is an acid. Does the anion contain oxygen? So the anion is everything that's not a hydrogen. So this is the anion here. Yes, it does contain oxygen. Okay, so yes. Check the ending of the, so this is the back of the periodic table again. We're checking the ending of the anion. So we look for CO3 on here. Okay, I found it about, 2/3 of the way down the page. It's called carbonate. Carbonate. So Carbonate, ATE. So we check the ending. It's ATE. 8 becomes ic. So we're going to say carbonic acid is the name of this substance. Okay, so as usual, you can try using this periodic table. Let's do one of these. We'll do this one. Tell me the name of this acid using this chart. All right, so here's some more practice, okay? HF, all right, so HF is, does it start with an H? Yes, okay, so it's an acid. Does the anion contain oxygen? It was HF, so there's no oxygen, just hydrogen and fluorine, so no. If it's in water, it's hydro, plus the root. The root comes from the name attached, of the element that's attached to the hydrogen, and then ic acid. So here we go. Hydro, it said. And then this is fluorine, so the root of fluorine is that. We just kind of take off the end. And then we turn it to ic acid. So hydrofluoric acid. HCN, okay, let's see. Does it start with an H? Yes, it's an acid. Does the anion contain oxygen? No, it does not. HCN, no oxygen. So hydro, I got to figure out what to call the CN part, and then ic acid. So hydro is there. CN, so there's 3 elements in this. I think that's going to prompt me to look at the periodic table. CN is the 3rd one down. It's cyanide. So hydrocyanide, IDE gets changed to ic acid, according to our chart. Now this one is a little tricky because it looks very similar, but it doesn't have AQ after it. So hydro is still there. Hydro is still there only if it's in water. This says if it's not in water, we're going to name it like a binary thing. So that's this green box in the bottom left. So you have a binary compound, HCN. Is there a metal present? Oh, it's not a binary because there's 3 elements, right? So the polyatomic ions, that's going to make me look at the back of the periodic table. Okay, so we got to name it like a binary thing. Okay, so hydrogen is the first thing. And then we just use the name from the back of the periodic table for the CN, so that's cyanide. Hydrogen cyanide. This is a gas. It's not an acid. It is very toxic. It's a nerve agent, but it's not the same thing as what you get when you dissolve HCN in water. These behave differently. Okay, so this one, okay, is the first letter in H. Yes, it is. Does the compound contain oxygen? Why, yes, it does. It has 2 oxygens. So I'm looking at the bottom one down here. Okay, so yes, it does. Check the ending of the anion. Okay, so, whoops, sorry, I keep going the wrong way. C2H3O2 is the anion, everything that's not that first hydrogen. And so I look on the back of the periodic table, and I see that the name of that is acetate. And acetate can be written in 2 different ways. It shows us both ways, but here it's C2H3O2. So the ending for that is ATE. So we're going to follow this path. ATE becomes ic acid. 8 is icky. So this compound would be properly named acetic, ATE, gets canceled, acid, acetic acid. So that's the name of that material. It's a really common acid. Now the other kind of question we're going to have is going the other way. So we get a formula and we need a name. That's one kind of question. In this kind, we get a name, and we need to get to the formula. This is very similar to what we have in lab, so we really do need to practice that. So us acid, us, O-U-S, occurs way up here. Us acid. It's right here. That means the ending was I-T-E. Okay, so if I just change this, N-I-T-R-I-T-E, nitrite. Now, a nitrite is not an element. It is one of the special groups on the back of the periodic table again. So we flip it over, and we see about halfway down, a nitrite is NO2 minus. Now I know this is an acid, so it means that the anion is going to be connected to hydrogen. So if I have hydrogen and a nitrite, the hydrogen is always a +1. Nitrite has a -1 charge from the back of the periodic table. So these match. This is perfectly great. And I know it's AQ because it says acid. Okay. The next one is hydrogen acetate. So hydrogen is just an H. This is named like a binary thing. So acetate we saw just now in acetic acid. Acetate is C2H3O2. This is not aqueous, because if it were aqueous it would have been called acetic acid. So it's a liquid, as it turns out. I would accept solid, liquid, or gas. I don't really care, but just not aqueous, okay? If you don't remember that hydrogen acetate is a liquid, that's okay. Finally, we have this one, hydroiodic acid. So the key here is hydro and ic acid. We only see hydroic here. So that means it's something that had no oxygen, because the answer here was no. So no oxygen. If we have a hydro, there's no oxygen. So it's just going to be hydrogen with the root thing, iode. Well, iode sounds like iodine, and iodine is I. Iodine is a halogen, so it's in group 17. It means it has 7 valence electrons. It's going to steal 1. Hydrogen's always a +1. So I need one of each of these. So that's what hydroiodic is. Okay, the final classification of things that we're going to learn to name is called hydrates. Now hydrates are kind of cool because what they are is a solid thing that has water stuck inside of it. So here's a picture. This is H2SO4 with 4 waters stuck to each one. So here's our S, here's our 4 oxygen, and these little dotted lines are showing us how the waters are attached. So there's 1 water attached here, there's a second one, there's a third one over here, here's the 4th one. So you have 4 waters that are stuck on every single one of these H2SO4 things. Okay, that's pretty cool. This is a solid material because it's arranged geometrically, and we said that was a characteristic of a solid. Okay. It turns out that you could bake these waters off. You put it in the oven for a while, those waters will evaporate. And when it does, it changes the properties of the substance. It might change the color, it might change the melting point, it changes all the properties. Okay, so hydrates are pretty neat. You've probably seen them in your regular life, like things that change color when they absorb water are always hydrates. So this substance up here is a picture of something called cobalt-2 chloride. The blue one on the left has no water in it, so we call that anhydrous, an meaning none. Okay, so it's blue. When it absorbs water, as it turns out, it absorbs 6 water. So the formula for that is written with a big dot in the middle, 6 water. Okay, this stuff is purple, so it's really kind of cool. It goes from being blue to purple. So you know when it's absorbed a whole bunch of water from the air or whatever. This big dot is what tells me it's a hydrate. So when we name this thing, it's going to be named with the word hydrate right in it. So for example, this H2SO4, this is going to be, it's not AQ, this is a solid, we said. So we're going to name it as hydrogen sulfate. And then I have to say how many waters are stuck on there. Tetra is our prefix for 4. And then I put hydrate. Or up here, this one's going to be cobalt-2 chloride. When we've got the 6 waters, we're going to say hexahydrate. So that's the purple one there. All right, I want you to name this stuff for me. All right, so this is our practice for that. And this is actually something you can buy in the pharmacy. You've probably used it before in your life. The commercial name is Epsom salts. But if you look on a bag of Epsom salts, it will actually show you this formula, and sometimes it even has the name right on it. All right, so name it right here, please. Here's where you put the name, and I will grade that when you turn in your notes. All right, So in class next week, we are going to look at that naming sheet I gave you. You need to practice it between now and then, and we're gonna correct it so we know what mistakes we have made. All right, and this is going to help immensely with writing your lab report. So hopefully you've watched this video, you've done the practices. You can always come and talk to me. Naming is not easy. I also strongly recommend you do other problems, either from the practice tests on Blackboard, or you can do problems from the textbook. The colored ones have answers in the back. If you want to see a tutor and practice this, send me an email and I will give the tutor a worksheet, or I'll send it to you. And you can get a few points for doing that as well. Okay, so lots of opportunities to practice. Make sure that you do. Okay. Also remember my tip that Google is going to mislead you. There's many, many ways to name things, and using Google is not a very reliable way of ensuring you're getting the right answers. So practice these, and come and see me when you have questions.